So welcome back to the next concept, which is the sum of the first n terms of a GP. Now, this formula has always been a formula that, is very hard for a lot of students to grasp, right? So I'm going to be explaining this using a very general sequence of general GP to explain to you how we actually derive it. Because if I actually sub in values, right, you'll get a little bit confused. So I'm going to be using a very general sequence over here that I will draw to show you why. Okay, so we know that a GP is essentially a sequence, right? But what makes a sequence a GP? Well, it's every consecutive term has a constant difference, right? And the constant difference of a multiple. So every difference is actually a multiple. Different from an AP, each term in a GP has a difference of a constant multiple. So you multiply it. Now, let's just use this as an example. Consider this GP whereby my first term is A, and therefore my next term will be AR, my next term will be AR squared, this will be AR cubed, this will be AR4, and then it goes all the way until AR n minus 1, right? You can see that the difference is times R, times R, times R, times R, and then it just goes on and on and on and on and on. So we know that the general term for this is just A times R n minus 1, right? Because A over here is my T1, and then I'm multiplying a constant difference of R to the power of n minus 1. So when we say the sum of the first n terms of a GP, right, we are essentially finding the series of a GP. Because remember, a series is just a sum of the terms of a sequence. So let's say Sn. N is essentially T1 plus T2 plus T3 all the way until Tn, right? And you know that this is T1, T2, T3, T4, T5, and then this goes all the way until Tn. So we are essentially taking A plus AR plus AR squared plus AR cubed plus AR4 all the way until ARn minus 1, right? We are essentially adding them all the way until ARn minus 1. So with that said, right, how do we derive the formula, which I will give you at the end of this introduction section? But I'm trying to build intuition here. That's why now I'm not like giving it to you directly. So we can see that the first step, we can actually factorize out the A, right? A, here I'll have 1 plus R squared plus R cubed all the way until Rn minus 1. Now, to generalize this and express this in terms of n, I'm just going to let this be Tn. Okay, so Tn can be written as 1 plus R squared plus R cubed plus dot 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 plus Rn minus 1, right? We can like use substitution. Basically, we just represent that whole thing over there as Tn. So what happens when I multiply R on both sides? So imagine this. If I multiply R on both sides, I will get Rtn equals to, because I'm multiplying R on both sides, I will have R times everything that's originally there, right? Which will give me R plus R squared plus R cubed plus R4 plus all the way until plus Rn. So what happens when I take Rtn minus Tn? What happens when I take this thing over here, subtract away this thing over here, right? What happens? So you realize that when I do that, I'm essentially taking my R plus R squared plus R cubed plus R4 all the way until plus Rn, right? And I'm subtracting away 1 plus R squared plus R cubed plus all the way until plus Rn minus 1, right? And this, you realize that it actually strikes out a few things. So you realize that this whole portion over here actually strikes out this whole portion over here, right? This whole portion here, feel free to pause the video if you need. This whole portion here actually strikes out this portion here. And what's left for us is essentially just Rtn minus Tn equals to Rn minus 1, right? And then on the left hand side, we can actually factorize out the Tn to give us R minus 1 equals to Rn minus 1, which we can derive it as Tn equals to Rn minus 1 over R minus 1, right? So what we have just done is that we have just transformed this whole thing over here into this. And why do we want to transform it in this way? Is because in the exam, you first and foremost, you wouldn't want to, write out every single term inside the sequence, right? Imagine if your sequence has 1,000 terms. How are you going to add 1,000 terms together, right? You can't write it out. So we need a compact way of writing it. And secondly, this allows us to sub in the values directly instead of manually computing every single value in our calculator. So which means that this over here can be written as A times R to the power of n minus 1 over R minus 1, right? Alternatively, you also can write it as A times 1 minus Rn 1 minus R. These two are equivalent to each other, right? So these two are the same. But as a rule of thumb, right, when will we use the first one and when will we use the second one? We will use the first one, use this when R is bigger than 1, okay? And then for the bottom one over here, we'll use this when R is less than 1. And recap, R over here is the common ratio. So this over here is actually the formula for the sum of the first n terms of a GP, which is a times r to the power of n minus 1 over r minus 1, or 1 minus r to the power of n over 1 minus r. Okay, and what I've just done is shown to you how we actually derive the formula. Now, I'm sure that your school, your tutorial notes will give you this formula straight, right? And maybe they will have some notes inside there, maybe the appendix that explains to you how this is being derived, right? But I'm hoping that by explaining it to you and showing you, in person how it's being derived, it builds intuition inside of you. Because the truth is that this formula over here is not given to you in the exam. So if you suddenly blank out, right, the second best thing that you can do for yourself, if you blank out and then you forget what you memorized, is to remember what you understand intuitively and use that intuition to derive the formula for yourself. Okay, so this is how it works over here. Okay, so yeah, with that said, we are going to use the two formulas that I just underlined over there to actually tackle this two mastery questions over here to make sure that you really understand the concept of a GP. So feel free to pause this video, to tackle this question right now. If not, right now, I'm going to be jumping into this question over here. So it is given to us that we have a GP. So I know that a GP has a general term of Tn equals to T1 times r to the power of n minus 1, right? So I'm just going to let Tn be the general term of this GP. Tn is T1 times r to the power of n minus 1. And it's given to us in the question. T1 is 1024, right? And therefore, we can just sub this back inside here later on. We are also given that T2 is 512. Which means that we can find what's r already, right? And then we know that the last term, so t last is 1. So they want us to find the sum of the geometric progression. The thing is that this last over here is something that I don't know. So I need to find out what is this value of the last term, right? Because this is not an infinite sequence. Because if it was an infinite sequence, then there wouldn't be a last term, right? So given that there's a last term, means that this is a finite sequence or a finite GP. Might call it that. So before that, let's first figure out what's our r. So Tn is 1024 times r to the power of n minus 1. T2 can be written as 1024 times r to the power of 2 minus 1, which gives me 512. So this is 1024 times r equals to 512. So from here, it's quite clear to see, right, that r is just 512 divided by 1024 and r is half. So from here, we can derive that the general term Tn is just 1024 times half to the power of n minus 1. So how do we figure out what is the n value of the last term? So the n value of the last term, how do we derive this? We can just let Tn equals to 1 and then just solve for it, right? So 1024 times half to the power of n minus 1 equals to 1. So half to the power of n minus 1 is 1 over 1024. Then from here, what I can do is I can, either use laws of indices to simplify this, or I can just use logarithms. But just to make things simple, I'm just going to use indices over here. So over here, I can write this as 2 to the power of negative 1, n minus 1 equals to 2 to the power of 10, negative 1, right? And therefore, this is 2 to the power of 1 minus n equals to 2 to the power of negative 10. So from here, I compare. 1 minus n is minus 10. So therefore, n is 1 plus 10 and n is 11. So essentially, this last over here has a value of 11. So they want me to find the sum of the GP, which is essentially the sum of the first 11 terms, right? Because the GP only has 11 terms. Therefore, the question answer would just be, therefore, S11, because that's all the terms that it has, using the formula above, remember, is A times r to the power of n minus 1 over r minus 1, given that the r is bigger than 1. But in this case, my r over here is lesser than 1, so I will use the formula of A, 1 minus rn over 1 minus r, right? I'll use the other one instead, because now my r is smaller than 1. And my first term is 1024. Here is 1 minus half to the power of 11, because I have 11 terms, right? And then below will be 1 minus half over here. So you just punch this whole thing into your calculator, and you'll get a final value of 2047 over here as the final answer to this first question over here. Okay, so yeah, that is basically how we actually apply this formula above in this question over here, and that's for the last portion. But before that, we actually need to solve for the n. Okay, so I hope that this is a good recap for you in terms of finite, infinite sequences. Okay, if not, we'll jump into the next question right now. So before I get into this question, just want to mention that if you are looking for more practices after this, for this chapter or any other chapter really in the whole syllabus, and you want to get access to my library of more in-depth questions, exam standard level questions with my exact video explanations, just like the ones you're seeing on my YouTube channel, make sure to click the link in the description under this video if you want access to the library. Okay, if not, feel free to pause this video right now to tackle this question over here, and if not, we will actually tackle this question together right now. So they want us to find the least number of terms of the geometric series. So the reason why they say it's a geometric series is because they already add up the terms together. Okay, so if they did not add up the terms together, if it's simply just 2, 3, 9 over 2, 27 over 4, right, like that, right, then this will be considered as a geometric progression, right? But since they already add up, it's a series. So they want us to find the least number of terms. So they want us to find the least value of n for which the sum exceeds 48. So to do that, I must first figure out what's my Sn formula. And I know that for a GS, right, geometric series, the Sn is just a times 1 minus Rn over R minus 1, or a Rn minus 1 over R minus 1, right? I show you how to derive this formula earlier on. But it depends on whether your R is bigger than 1 or not. So we need to first observe what's the pattern over here. So I know that this is T1, T2, T3, T4. T1 is 2, which means my A value is 2. Now how about my R? You see, from here to here, I times 1.5. From here to here, I times another 1.5. And then from here to here, I times another 1.5 once again. So we can see that my R has a value of 1.5, which means that my R value is bigger than 1. And therefore, I would choose this over here to make things a little bit easier for myself. Well, honestly, if you use both, right, both is fine. Like, it's really fine. If you use the first formula over here, even though R is bigger than 1, it's fine. But personally, I would prefer to use the second one because it just looks nicer on the paper. Oh, and I just realized I wrote this in the wrong direction. Yeah. Okay, so I'm just going to use the formula. So we know that Sn can be written as 2 times 1.5 to the power of n minus 1 over 1.5 minus 1, right? And this will eventually give me 4 times 1.5 to the power of n minus 1 over here. So they want us to find the least number of terms for which this Sn is bigger than 48. So for Sn to be bigger than 48, I just need to have 4 times 1.5 n minus 1 bigger than 48. So I divide the 4 over. Since it's positive, the sign will flip, right? So here would be 12. So 1.5 n is bigger than 13. So to find the value of n, I just need to log both sides. So n log 1.5 bigger than log 13. But before that, right, before we actually, bring the log 1.5 over to the other side, this is a very important thing that you need to check, right? Log 1.5, when you key into your calculator, you get a value of positive 0.176091, ... Which means that even though we divide log 1.5 to the other side, it's okay, right? Because the sign won't flip. But if it was negative, let's say this value over here is negative, you must make sure to flip the sign. So this is a very big case mistake that I see a lot of people make. Okay, but now you know. So since this is positive, I don't need to worry about the sign when I divide it over. It's just log 13 over log 1.5, right? And then over here, I'll get a value of log 13 divided by log 1.5. I get a value of 6.325943 ... right over here. And therefore, the n minimum would be 7 because, it cannot be a fraction, right? So that's the answers to this. And just make sure that you perform this check because a lot of secondary and JC students still make this mistake whenever it comes to inequalities division. Okay, so any questions, let me know in the comments below. If not, that's it for this concept over here and the example question. In the next one, we'll be talking about how do we actually test for the presence of a GP similar to that of an AP, right? And once you understand this, click on the next video and I'll see you there.